So my name's Torry Steed. I'm a product marketing manager at SMART Modular. I'm primarily focused on the CXL product lines that we have. So that's going to be the focus of the presentation today. We've had some excellent talks earlier already about some of the benefits. So I may kind of move through quickly some of the benefits because I think that's been covered very well. But first, a quick introduction to SMART. So Smart Modular is one of the divisions of Smart Global Holdings. So SGH is the ticker symbol for Smart. And Smart Modular focuses on advanced memory solutions. And we have been involved in working on CXL development for the past 3 years or so now. You can see some of the other information about the company there. But the only other thing I'll mention is that we have a sister division that involves or includes Penguin Solutions, and Penguins is a system um, developer, and so there's actually a lot of good synergy between Smart Modular that makes the components and Penguin that makes the kind of end system solutions. So moving right on to CXL. So I think we can skip over this. Essentially, you've seen this several times, but the gist is that CXL is a protocol that operates on the physical PCIe lanes and or three new protocols really. And depending on how you combine those protocols, you get different types of devices. The first to hit the market is these memory expansion devices, which everyone's been focusing on. But I do want to say that we do expect to see CXL be adopted to not just accelerators, but even storage and networking and everything else going forward. There's advantages. So do expect to see that, but that's a little ways out. Right now, we're focusing on memory expansion. Okay, so some of the advantages, I think this was hit really well by Ravi earlier, some of the advantages, but I'll just do a super high level version of it. Obviously, increased capacity is a big one. Once you fill up your DIMM sockets, you're kind of out of room for that particular CPU. So by connecting memory to CXL, you can obviously increase your memory capacity. So that's a big one, has a number of performance benefits for many different applications. The next one is actually you can reduce the cost. So there's a question earlier about the cost difference between a CXL memory module versus direct attached DRAM, a DIMM. And the reality is that the CXL module is always going to be a little bit more expensive. And that's because the CXL module includes a controller, right? There's a controller that converts that serial interface to the parallel interface used to talk to the DRAM. And that controller is going to cost money. But Robbie made a really good point. When you look at the overall system cost, you can actually bring the overall system cost of the memory down. And I'll talk. I think that's been covered a little bit before, but I'll cover that in more detail coming up on how that would work. And then the final one that I think has also been covered very well is the increased performance just in terms of bandwidth performance. You essentially, by adding CXL memory, get that additional memory lane, that super highway to talk to memory in a different way. And you get even additional benefits, again, as Robbie covered really well with the interleaving options. So that's pretty exciting. But even though the latency of the CXL devices is higher than the direct attached DRAM, you can get an overall boost to the system using CXL. Okay, so these are some of the applications that are driving the development of CXL or the need for CXL memory expansion. Obviously, artificial intelligence is a huge one that's been covered in great detail. But even just applications where you want to do in-memory database, right? It's application's been around for a very long time. That can get significant benefits from CXL. As well as video processing, that's a growing field with security deployment of security cameras. And then even in biotech, where DNA sequencing machines are being used, the cost of those has come down dramatically in recent years. And they generate lots of data, and you need to process that data in real time. So having large amounts of memory for those applications is highly valuable as well. So a lot of different things driving CXL. The real point of this is it's not just AI that's driving the need for more memory. So it's really kind of all coming together. Okay, this is how we expect to see CXL being adopted in the industry. The first method, which we've talked about in great detail, is adding memory to the server itself, right? Direct attached CXL to the CPUs. And there's a lot of benefits to this that we just covered. But we also see in the future adding CXL expansion to being disaggregated, right, through that memory pooling and sharing method. So we see both of those being adopted going forward, and starting with the direct attached memory and moving to the pooling and sharing. But even during that time period, we will still see direct attached memory. We will still see direct attached DRAM, as was mentioned earlier this morning. It will become kind of this tiering, this multiple tiers of memory that all work together in conjunction to fill in that gap in the memory tier. All right, so when is it all going to come together? The good news is that the spec is largely done, right? The CXL 3.1 spec was released the end of last year. It's continuing to be refined, but added features and clarifications, but it's largely done. We do have CXL controllers from a number of different companies that I think we're going to hear more about coming up later today. But those are available now as well. Most of them are supporting the CXL 2.0 features, but that's more than sufficient for both direct attached and memory pooling behind a switch applications. In 2025, we do expect to see kind of the next generation of CXL controllers emerging that will support the CXL 3.x standard. So we'll add those kind of additional capabilities there. And then here's to the major CPU vendors, their kind of very rough releases and which versions of CXL those support. We do see that direct attached memory going into production this year. We ourselves at SMART have a couple of products that I'm going to be talking about that will be released and in production this year. And then we do see that memory pooling kind of taking off more next year as a second phase of CXL adoption, but they will exist in parallel and they will go forward together, we believe. Okay, so let's talk about what SMART's actually doing. So we've got several product lines that are all looking to be released in 2024. The top row there shows our add-in cards. So those are in the kind of the traditional PCIe add-in card form factor, similar to like a graphics card or a network interface card. And we have two that are in the lab and in bring up now. We have an 8-DIMM add-in card as well as a 4-DIMM add-in card. Both of those are DDR5 solutions. We are looking at doing DDR4 add-in cards as well, but it would be kind of late this year is when we would be introducing those. And we are looking also at a low profile card because certain 2U systems, this is a much friendlier form factor. So we're looking at introducing those as well. We do also have the E3 form factor similar to what Micron showed earlier. There's a couple little differences in terms of capacity and whatnot. So I'll talk about those in a minute. But then we're also introducing a non-volatile version of a CXL memory expansion device. And those of you who are familiar with NVDIMMs might be aware that those are not moving forward into the DDR5 timeframe. So instead, what's happening is we're going to be introducing NV capability on a CXL device, and we're working with the industry to get that standardized. The good news is that the CXL spec already includes a lot of the hooks that are necessary to make that work. So that's making good progress. All right, this is the 8-socket add-in card. So you can see from the block diagram that in order to get 8 DIMMs on this card, we use 2 CXL controllers. Each is a by 16 controller, but because they're working together on the same mechanical slot, which is limited to a by 16, they operate in by 8 mode. So you essentially have 2 ports on this mechanical connector. Each is a by 8 talking to one of the controllers. And then behind that, each has 2 channels with 2 DIMMs per channel, getting you up to the total of 8 DIMMs on this card. So the important note about this is this does require systems that require or that support bifurcation of the bus, right? So you have to be able to plug this into the system, and it has to be able to identify that there are essentially two devices on that port. But that is supported by the latest Intel and AMD systems. Okay, it's a full height, half length, dual width card. those DIMMs sticking out horizontal to the PCB require a double width slot. Also, if you saw my form factor presentation yesterday, you might have seen that the maximum power delivery through the edge connector is typically 75 watts. Well, each of these DIMMs is probably on the order of 10 plus watts itself, and we have 8 of them, so you can see immediately that we've exceeded that 75 watt limit. So you might notice there's an auxiliary power connector here. This is a standard PCIe auxiliary power connector that you might see on a graphics card, for example. But that's necessary to get enough power to this device for it to work. Okay, moving on. This is the 4-DIMM add-in card. It's a little bit hard to see, but there are 2 DIMMs stacked on top of each other facing down towards the connector, and then there are another 2 facing up. This uses a single CXL controller with 2 memory channels, also DDR5. And the advantage of this is this does not require the bifurcation, right? You get the full by 16 interface talking to the 4 DIMMs behind the controller. Also, this one fits in a single width add-in card space. So a lot of times in the system, they're installed horizontally, and a single width has some advantages there. Not much to add there. This one is, like I said, this is one that's in feasibility now for us. It's a low profile card. It's also DDR5, but because of that low profile, we need to use 2 CXL controllers. They'd be the by 8 controllers so that we can get smaller, smaller dimensions in order to have this fit. So this would be a bifurcated bus as well. But otherwise, it's very similar to the 8-DIMM. It's just smaller, just half the height and smaller. Okay, so this is the kind of one example of a way to look at the overall system cost when you're considering CXL. So this is an example where you're trying to design a system that has 1 terabyte of memory per socket. And so in order to do that with a system that supports 8 DIMMs per CPU, which is a pretty typical loadout for DDR5, you would need to populate it with 128 gigabyte DIMMs in order to get to a terabyte. And because 128 gigabyte DIMMs right now require stacked or 3DS DRAM, soon we'll get 30. We're going to have 32 gigabit DRAM coming out, and that will move the bar up a little bit. But for today, you need the stacked 3DS DRAM, and whenever you introduce that component, there's a significant price increase. So you can look at DDR4, DDR5 DRAM modules, and you'll see when you hit a certain density, the price spikes, and that's why. And if you can instead populate your system with the more cost-effective modules, in this case, this example, that'll be the 64 gigabyte modules, you get a significant cost savings. So you could populate it with twice as many, instead of 828 gigabyte modules, you use 16 64 gigabyte modules plus an add-in card, in this case, an 8-DIMM add-in card, you get a significant cost savings, right? Even with the addition of that card, just because of that price difference in the memory. This is the E3.S CMM that SMART introduced last year. It's a 64 gigabyte capacity. It is DDR5 behind the CXL controller. So as Robbie mentioned from Micron, there's different choices you can make there. This example is a DDR5 module behind a by 16 interface. So this is a little bit more niche just because it's a little more rare today to find a by 16 interface in the front of the systems to support an E3 module, but it does have some advantages in terms of bandwidth if the system supports it. We are looking at releasing a new version of this that will be using 24 gigabit DRAM, so the capacity will increase to 96 gigabytes on that version. And when 32 gigabit is available, it will support 128 gigabytes. Okay, I want to spend a little bit of time on this one because there were some good questions before when I've talked about this device. So we are also introducing an NVCMM, so a non-volatile CXL memory module. And this device has both DRAM as well as NAND on it. However, the host system during runtime only accesses the DRAM. So it acts just like this device during runtime. The host system has access to the full, in this case it's a 32 gigabyte module, so it has access to the full 32 gigabytes. The NAND is only used in the event of a power failure. And if in the event of a system power failure, the host notifies the system that, or the NVCMM that power is being lost, and the DRAM data is copied into the NAND flash using a smart NV controller. And it uses onboard energy source module. That's what ESM stands for. And that is made up of supercapacitors that power the module long enough to do that data transfer. Then when system power comes back, we copy the data back from the NAND into the DRAM and let the host know that everything is back up and running. And as far as the host system knows, data is never gone.
Hey, Torry, we have a question for you.
Yeah.
Which use cases are driving CMMM? NVCMM.
NVCMM. So the primary ones that
there's a second part to the question. How
okay,
does tail latency impact the workloads and application that you mentioned?
Okay, so for the first part of that question, it's the same use cases that you would see for NVDIMMs in the past. So it's write caches, it's in-memory databases, it's database tables that like logging so that you can rebuild, it's checkpointing. Those type of applications are driving NV. And then, sorry, repeat the second part of the question for me.
Yeah. The second part is how does the tail latency impact the workloads and application that you mentioned?
The tail latency. I'm not sure I can answer that offhand, so I need to look into that a little bit.
I think I can help.
Oh, please, please.
There is no tail latency because he's executing always out of DRAM. Like he mentioned, you only use that NAND flash in case suddenly power goes away.
That's correct.
So there's no tail latency. It is going to be. So in fact, the question there is CXL by 8 controller. So don't you need two DDR4 channels behind it?
Yeah, this block diagram is not as detailed, so
okay. So it is two DDR4, right? So that will sustain the bandwidth.
Yeah.
Yes.
Yeah.
With the given capacity, single channel is good enough, 32 gig.
That's right.
No, it's not capacity. Otherwise, you won't saturate the CXL by 8 bandwidth, right? 1 by 8 will need two DDR4 behind it or one DDR5 behind it. That's my question. That was my...
I mean, the follow-up question to you.
Yeah, please.
Gig? Why can't we have higher capacities here? Is it because you are taking the backup at that time duration is limiting you to have 32 gig only, or? Yeah.
Right. Yeah, no, that's a very good question, and you're starting to hit on it. So the reason we can't have increased capacity is because we're integrating the energy source module, the super caps. They are quite large, large-ish, and they take a portion of the PCB. So it's PCB space limited. We could go to higher density DRAM. So this is our first offering of the NV device. It's kind of the first generation. We do have architectural plans to go to DDR5 and to increase capacity. We have some ideas about how we would be doing this, but initially it's limited by board space is a big one and capacity of the ESM. Yeah, great questions though. And thank you, Anil, for helping me put clue into the first question. All right. This is some of the reasons why SMART is well situated to develop these CXL modules. We have excellent controller partnerships with many of the companies that are developing controllers, and we've been making complex memory modules for a long time, including NVDIMMs, which have controllers and firmware, and DRAM, and we are DRAM and NAND experts. And we have been working on many of the other protocols. I think in the presentation this morning, it was mentioned how many of these other protocols are converging to CXL, and we've been involved in that now for many years. So it's a good fit for us to develop these products. By way of summary, you can visit our website for some white papers and some additional information on these CXL products that we're developing, or you can reach out to me directly, and there's my contact information there. Okay, and that's it, Frank.